Alright guys, in this video we are going to review some linear regression, which was all about our scatter plots. This was way back in Outcome 2, so if you still have your Outcome 2 notes, you could look back at Outcome 2. Our next chapter, chapter 27, works with these scatter plots again, so I want to make sure that we have a nice kind of recap of everything we know about linear regression. So our scenario says new state requirements force students to take a high-stakes math test in order to graduate from high school. Faced with such a pressure-laden situation, many students become very nervous, which may interfere with their ability to perform well. Concerned about this test anxiety, a researcher enlists 24 student volunteers for a study. A psychologist interviews them before the math test, assessing their anxiety levels on a scale from 1 to 10. The table shows the anxiety levels and the exam scores. So here we have our different students, we have their anxiety levels, and then we have their math test scores. So the first thing that we want to do is enter the data into our calculator and make a scatter plot. Once we have the scatter plot on our calculator, we'll go ahead and sketch it below. So I'm going to start with inputting this data into my calculator. I'm going to put anxiety level in L1 and math test in L2. Now the reason that I'm doing anxiety level in L1 and math test score in L2 is so that when I graph the scatter plot, I can use their anxiety levels to make some kind of prediction about their test score. So I'm going to use anxiety to predict test score. You could have it switched the other way around, but I think it makes a little bit more sense to use that anxiety level to help figure out how well or how poor they're going to do on that test. So I'm going to go to my stat, I'm going to hit edit, and I'm going to clear everything out in here, and I'm going to put all of these anxiety levels into L1, and then I'll put the math test scores in L2. I'm going to go ahead and pause my video while I type these in. Go ahead and do the same. Once you have everything typed in, go ahead and press play. Okay, I have all of my data in my L1 and L2. So at this point, I can go ahead and use my calculator to create this scatter plot. To get to the scatter plot, I'm going to go to my stat plot, so second y equals. I'm going to be editing this first plot here. You do want to make sure it's on, and then the first option here is a scatter plot. Okay, make sure that your X list are those anxiety scores. That's L1, so I'm going to change this to L1. My Y list can stay the test scores of L2. Okay, once we have those, we can go ahead and press zoom 9, and it gives us this scatter plot. So I'm going to go ahead and sketch this picture here. It doesn't need to be perfect since it does just say sketch. Okay, we do want to make sure that we have labels. So I'm going to label my x-axis as anxiety level. Y-axis will be math test. Okay, I'm going to go ahead and just kind of roughly sketch what I see here. Okay, we should also have a title here, so I'm just going to say high stakes math test. You could say math test and anxiety level, doesn't really matter as long as you have some kind of title explaining what data we're looking at. Okay, number 2 says, does there appear to be an association between anxiety level and test score? We want to describe what we see in that scatter plot. Okay, when we learned about scatter plots at first, we had a nice little acronym to help us remember how to describe the scatter plot. That acronym was DFSU. Don't F stuff up. Okay, D stands for the direction, so we're going to talk about whether this scatter plot is positive or negative. The form, whether it's linear or curved. S is for strength, so that's how strong or weak things are. Remember, a scatter plot that's very tightly clustered together would be strong, more spread out is weak. And then the U in DFSU stands for uniqueness. So I'm going to start with, again, putting this into context. I'm going to say the scatter plot of anxiety levels and test score is directionally, it's kind of hard to tell, there's not much going on here, but if I had to pick a direction, I would say that it does look like it's moving more in the negative direction than in the positive direction. So I'm going to say that the direction is negative. It doesn't look curved or straight, so I'm going to say here roughly linear. And as far as strength goes, these dots are quite spread out, so I'm going to say very weak. Okay, I'm noticing one point that I think is maybe a little bit unique, and it's this guy over here. We can actually find that exact point in our calculator if we hit trace, and you'll see my cursor started way over on this side, so I'm just going to kind of scroll around here until I get to this point that I think is my maybe unique point. There we go. So this person had an anxiety level of 4, which was quite low, but they only scored a 29 on the test. I think that point is maybe a little bit unique, so I'm going to go ahead and write it down. There is one unique data point at 429. This student had a low anxiety level but scored lower than I expect. Okay, most of those other low anxiety levels scored quite high, so I'm a little bit surprised by that point kind of way down here. If you don't have any outliers or unique points, you're okay just to say doesn't look very unique. There's nothing kind of unique about it. Okay, number 3 says find the correlation or the R value. Remember that this R value corresponds to your strength. Okay, so R always corresponds to the strength of your scatter plot. Now, to find our R value, what we're going to do is run a linear regression in our calculator. So I'm going to go to my stat, calculate, and I'm looking for linear regression. You could go down to number 4 or number 8. They're both going to give you the same thing. Make sure that your X list is L1, Y list L2, and I'm just going to go down to calculate. Now mine right now is just giving me the A and B value, which is fine for finding the linear equation, but right now I want that R value. If yours already says R and R squared here, you're good to go. Mine doesn't, so we might need to turn that stat diagnostics back on. To turn that on, we're going to go to mode, and I'm going to scroll down until I see stat diagnostics. Mine is off right now, which is why I'm not showing up with that R and R squared. So I'm going to turn that on. Then I can go back to my stat, calculate, linear regression, and it now gives me my R value of negative 0.52. So a few things that this R value is telling us It is negative, so that corresponds to my decision to say that the direction was negative, and an R value of 0.52 does correspond to this being quite weak. Remember that the strongest your R value can be is a positive 1 or a negative 1. If you had an R of positive 1, your dots would form a perfectly straight line in a positive direction, versus negative would be going down. Okay, so what does this correlation indicate? What does it indicate? It tells me the direction is negative and the strength is weak. So if you're stuck on that DFSU, it is nice to find that R value. It's a great way to find the direction and the strength. Okay, the next thing that I needed to do was find my R squared. Lucky for us, it's right there, so I'm just going to round this to 0.28. R squared is a little bit harder to interpret. When we looked at this R squared, we had just a little template that we used every time. I'm going to start with writing that template off to the left here. R squared tells us the percent. So I'm going to do R squared percent of the variation in your Y variable. So you're going to input whatever your Y variable there can be accounted for by the variation in your X variable. Okay, so an R squared of 28 here is telling me that 28% of the variation in test score, that's my Y variable, can be accounted for by the variation in anxiety level. Okay, essentially this is saying that the different test scores that we're getting, only 28% of those differences are because of the differences in anxiety level. This is quite low, which I think makes sense. There's a lot more that is going to impact your test score than just your anxiety level. So only 28% of the differences in this test score is due to the differences in our anxiety levels. Okay, next thing that we're going to do is create this linear model. We do have these values on our calculator already. The linear model is going to be just a straight line here, so I'm going to use my y equals ax plus b or mx plus b. Now remember, when we write this linear model, we do need to make sure that we're putting things in context. So instead of just y, I'm going to put whatever my y variable was. So my y variable was my test score or my math test. So I'm going to say math test equals my a value, which is right next to x, so that means a is my slope. So I have negative 4.49 times x, but instead of x, I'm going to put my x variable. So in this case, that was our anxiety levels. And then I have my b value, which is positive 91.66. Last thing that I want to add on here is a hat onto the math test. Remember that that hat is telling us this is a prediction. So this is just a model. It's not perfect. It's not telling me what's happening in reality. It's just a good guess of what's going to happen. So when I figure out what my anxiety level is, I can plug it in right here, and it's going to make a prediction of that math test. So again, remember that this hat means we're making a prediction. Number 6 says, is this linear model appropriate? We want to create and discuss the residual plot. Sketch the residual plot below. So remember that residuals measure how far your data is from this line of best fit. So we just created a linear model, which is the line of best fit. What we could do is take this linear model and graph it on our little graph here. So I'm just going to make a sketch, a guess of what I think is happening. Maybe it's going to look something like that. Okay, a residual is the distance that each point is from the line of best fit. So this point that's quite close would have a very small residual. This point that we said was unique would have a very large residual. The residual is measuring how far that data is from your line of best fit. So one thing we looked at was creating an actual residual plot. Once we have the line of best fit, which we did in number 5, we can create that residual plot in our calculator. To do so, I'm going to go back to my stat plot, so second y equals. And instead of L2, I want to change this into residual. To get to our residual, we're going to have to hit this list, which is above stat. So I'm going to hit second stat. And when I scroll down, I should see resid, which stands for residual. You can keep your picture as a scatter plot. Residual plots are basically just a specialized scatter plot. So I'm going to go ahead and sketch this. Okay, the only thing that we need to make sure is that we have this labeled as residuals. This is our residual plot. Okay, now when we make a residual plot, what we're doing is determining if that linear model is appropriate. Okay, there's two options here. If your residual plot is random, it means that the linear model is appropriate. So if residual is random, then linear model is appropriate. Your other option, if the residual plot has a pattern, then linear model is not appropriate. Appropriate. Ooh, spelling is hard. So, quick example, if I give you a random residual plot, it would look, it's just random, dots all over the place. Pattern would look something like this. Okay? There's a definite, very clear pattern there. The residual plot that we have here is looking quite random to me, so I would say a linear model is appropriate because the residual plot is random. We want to see randomness in that residual plot. Okay, we have a few more on the next page. All right, number 7 says interpret the slope of the line in this context. I'm going to just quickly jot down the line of best fit again. So we had our test score that we were predicting. We had negative 4.49 times the anxiety level plus 91.66. Okay, the slope of your equation is always the number that is next to the x variable. So in this case, this negative 4.49 is my slope. Okay, what's nice is we had a nice little template again for this. We said that the model predicts that for every additional x value, so we're going to input whatever our x is, we expect the y value to, we're going to say either increase or decrease depending on the sign of your slope. So if the sign is positive, then it's increasing. If it's negative, then it's decreasing by an average of blank. And this is where you would input that actual slope. So in this example, we would say the model predicts that for every additional, I'm going to put in my x value here, so this was anxiety. So I'm going to say for every additional level of anxiety, we expect here's where we plug in our y value. So our y value was that test score. So I'm going to say we expect the test score to, slope is negative, so I'm going to say decreased by an average of my slope here. I'm going to just say 4.49. I don't need the negative since I've already said that it's decreasing. We can just make this positive. And the last thing I want to do is put in a unit here. So I'm assuming that my math test was graded, I don't know if it's by points or if it's by percentage. So I'm just going to guess that it's in a percent here. So I'm going to say it'll decrease by an average of 4.49%. Okay, a few things to look out for. You do want to make sure that you include this, the model predicts. This is telling the reader that you understand this is just a model. It's not what's happening in the actual, in reality. It's just what we're predicting. Make sure you are talking in context, so you should not have x's and y's here, but you should have what those variables actually are. And don't forget an average with a unit. In number 8, we're going to be interpreting the y-intercept. The y-intercept is the other number in your equation here. It should be the number that does not have the x variable right next to it. Okay, when we're interpreting that y-intercept, we still start with the model predicts. That. Now, y-intercept is where this graph would cross the y-axis. Every time you're looking at a y-intercept, it means that your x value is 0. So we're going to say that the model predicts that when your x is 0, we expect y to be, and then this is where we would put our y-intercept. So for this example, we would say the model predicts that when your x value, which is your anxiety level, so the model predicts that when the anxiety level is 0, the student will have a test score, which is my y variable, of 91.66%. Okay, now this one makes sense. I think that it's definitely possible that if you are not anxious about this test at all, you could score a 91.66%. It's definitely possible. Sometimes when we interpret this y-intercept, we get something that doesn't make any sense here. For example, you might say the model predicts when the anxiety level is 0, the student will have a test score of -49. Well, they can't score a -49 on a test. So if you get a y-intercept that doesn't make sense, make sure you just add a little disclaimer on there saying this does not make sense in context of the problem. Okay, the last one here says, does this prove that anxiety interferes with student performance? The big keyword that we're looking at here is this proving. Okay, scatter plots show correlation. They can show relationships, but scatter plots can never show causation. They can never prove something to be true. So I'm going to say no here. Scatter plots show correlation or some kind of relationship, but they never show causation. The only way that we can prove causation is to run an experiment. We have not done a full experiment here. This was just kind of collecting some data. So my scatter plot here cannot prove that causation.